What's up, guys? Welcome to another episode of Botcraft. So, sorry if you've been waiting for the last episode or for this episode of Botcraft. I've been a little busy here lately with getting stuff situated and also doing a lot of research and doing some schematics. And it's basically going to be what we're going to talk about on this episode, where we're going to be working on building the circuit board that's going to control the rover. Um, Now you remember that in the previous videos we've been kind of doing things with modules, and while I could use the modules to control the robot and build a functioning um, rover with just all those modules by itself, and maybe just build like a little um, breakout board that connects everything together, that might be an ideal solution. But I think that a single board solution, or at least something with a little bit more logic behind it, might be a little bit more powerful and would give a little bit more opportunity to kind of make this rover do basically whatever we want. Now, this first revision of the board design is going to be a little bit different, or a little bit simplified, I should say. But I think there's a lot of neat features that you'll like and that I think will be worthwhile. So stay tuned. We're going to first cover in this episode the drawing or the design process of the board, looking at the schematics, the different components that I've selected for this device, and why I chose what I did, and why I decided not to go with other options, or what other options there were available for me regarding certain aspects of the design. So without further ado, let's go ahead and let's hop on the computer and we will take a look at what components I'm going to be using, and then we'll go over the electrical schematic that I've got so far. So let's get started. Alright, so the first thing I want to do is take a look at what microcontroller or controlling device that I want to use for this project. That's the first thing that I considered um, when I start working on the project. Everything else will kind of fall in line once you have this decision figured out. But until you know what you're using to control this system, then you're really kind of just beating around the bush, and you may end up going down rabbit holes you don't really want to go down and spending all kinds of time on stuff that you're not really sure about. So the first thing that I sat down and did was figured out what type of device I want to use to control this robot. So I have there's a multitude of different options available today as of the recording of this video that I could utilize to do this project. So let's look at the first option I took a look at. Here we have the ATmega 2560 Avr microcontroller, and this is the same microcontroller chip that you find in the Arduino Megas. So it's got a lot of GPIO. I mean, let's just take a look here. We've got 89 GPIO pins. As we know, it runs at standard 5-volt TTL logic level. You've got multiple serial interface ports, including SPI, UART, and I2C. And it's got multiple UART ports that you can use that are hardwire UART ports, and then you've got the software serial software serial ports that you can use in software. But as far as hardware ports, you've already got multiples available. So this is a very capable controller. It's the same microcontroller, like I said, for the Arduino Mega. So there's no question. It's a really good microcontroller. You got lots of GPIO. It's very capable. A lot of PWM channels. It's a very good device. There's one caveat though. My biggest concern is the cost. If you look here, the cost is $14 roughly for a single unit. And I'm planning on having this board manufactured, and I'm looking at JLC PCB as a manufacturer. And it's going to be a lot cheaper to get a mass quantity order of like 10, which is their default. But the extended price is $130. So it's a little bit more of an expensive processor, and it is limited. It's got limited memory of a 256 kilobytes, and it's got 8 kilobytes of RAM. So you're limited in memory space, and really the only best IDE to use here is the Arduino IDE. I kind of had plans of using the MicroPython IDE or programming language to control this rover, but that is flexible. But I'm not really too sure that I want to use this microcontroller, but I just wanted to kind of show it as an option for later revisions or something of that nature. I also thought about using this as a coprocessor to something like a Raspberry Pi. You know, having like a Raspberry Pi Zero attached to the board, and then just having this act like a coprocessor to that, and just run the peripheral hardware, and the Raspberry Pi do all the big processing stuff, which is also an option. But let's look at the other options. All right, so the next controller that I considered, and the biggest advantage, or the biggest thing that I looked at was processing power. You know, like we talked about with the 2560, it's got processing power, but it is limited. It's only an 8-bit microcontroller. So there's advantages, there's pros, there's cons to that. So the next microcontroller that I looked at was the M0 and also subsequently the M4 microcontroller. These both are ARM Cortex processors. Now, as you'll notice, they have less GPIO available. In fact, there's only, where is it? You just saw it. 38 GPIO pins available. So there's not as many as the 2560, which had 89. But the thing that I like about this is that it's a 32-bit microcontroller. So it's a lot more capable. You can actually use this with a memory chip to give you more memory, which you could also do with the 2560 if you wanted to. But this one's already been proven to be useful with programming languages such as MicroPython. There's a lot of focus around this microcontroller now because of the fact that it's a lot more advanced than the 8-bit microcontrollers. And also look at the cost. I mean, for just one unit, it's $3, a little over $3. But you know, that's a tremendous amount of reduction in cost versus what the 2560 was, which was $14 for a single unit, a little over $14. So this is a much more inexpensive processor, and it gives you so much more power. It's also got native USB support. So if I were to use this, then I wouldn't have to use a USB to serial bridge chip, such as like a CP20 or 2102. So it's got native USB support, so it can act as a USB device when you plug it straight into a computer. It reduces your hardware requirements because of that also. You still get the same serial interfaces that are available, such as the UART, SPI, and I2C interfaces. And like I said, it's just as capable as other microcontrollers. It's got a lot of features that are very beneficial. And a lot of the features are very promising. I like the fact that this is a newer microcontroller chip, so there's a lot of advances in this, and there's a lot more available today. So, you know, and like I said, this one and then the M4 processor, which is an even more faster processor, this one can run at a maximum of 48 megahertz, and the M4 processor can run at even higher than that. So they're a lot more capable, and it's made by the same people. I mean, it's the same microcontroller that you would have on an Arduino 101, I believe. So, or it's either the 101 or there's another one. Anyway, it's a very powerful processor. Now, it can only operate at the 3.3 volt logic level, but that's not a real big conflict in my opinion. It's easily worked around, and there's not really that many devices that I'm using that need 5-volt logic. So, and for the devices that I do, I could just use a single level shifter for that. So that's not a big issue. So a very strong candidate. In fact, I've briefly considered using this, like I said, with the last one as a coprocessor or as a second revision. If I were to redo this board and add more features, I might use this as the second revision. But this wasn't the design that I went with so far. But maybe you like this design better. Maybe I might rebuild this board and build it with the M0 or the M4 processor. I don't know. Let me know what you guys think about that. But this was a very big contender in my book. So now let's go over to the third and final option, which is the one I'm going with for right now, and see what you guys think about it. Alright, so let's take a look at this device. So I've chosen to go with the ESP32. The main reason that I've decided to do that is because this device is shown to be a very capable microcontroller. There's still a lot of development that's going on right now in the maker community, but I think that's a very good opportunity because the ESP8266 ended up being a very big success, and after it went through all the development stuff, it's fairly stable. There's still some quirks about it, but the ESP32 I have seen looks to answer some of those issues that were shown to be with the ESP8266. So this is the device that I'm thinking about using for the rover. Now I've got it pulled up here on Adafruit, and they are retailing it for about $8.95 for a single unit, and it does go down with quantity marginally. There's probably other vendors that sell the worm module, which is the full SoC. I'd rather just get the whole SoC, so that way the actual ESP32 module is already pieced together. I can easily put it together onto the main board as one whole board, but it just makes more sense to use the worm module SoC and just solder it directly to the board, and not have to reinvent that part. Just build the board around it to control it. This device does not have native USB support like the M0 processor that I was planning on using. But that's not a huge disadvantage. All I need is like a CP2102, and I've got a USB to UART bridge. And it's got its own internal flash, and you've got quite a good number of GPIO pins. You still got the same serial interfaces such as UART, SPI, I2C. You've got a lot of GPIO. You've got analog GPIO, digital GPIO. It's even got analog input, or analog outputs. I don't really plan on using those, but it's got them. So it's very, very capable, and I think there's a lot of potential for this device, even though it's still in the development phases. So I'm willing to work with the community, and I hope that people watching this might also consider working with the community, because that's how we make projects like this. How we get products out there. We play around with these things that are still in development and make them much better than the creators ever intended for them to be. So I've decided to go with this device. So I guess next we need to look at everything else that we're going to be using for this project now that we've figured out what device we're using to control the robot. Alright, so now that we've discussed what microcontroller we've decided to use, I've jumped over to KiCad to the electrical schematics that I've drawn, and this is what's actually taken me so long to make a video, because I've been trying to finish this up, and doing this in between work and everything is just, I don't get a whole lot of time to do this. But anyway, so as you can see here, I've drawn out the ESP32 module. Now, like I said earlier, the ESP32 module does not have native support for USB interface, but it has 2 UART ports. So for one of the UART ports, I've connected it to this CP2102, which is a USB to UART bridge. It's a fairly standard device, and it's cheaper than an FTDI chip, so I liked it. And its configuration that I did here is really just recommendations based off what the original manufacturer specifies as what should be recommended. Now, if this proves to be incorrect or proves to be problematic, I may have to make changes to the board later on. But I'm going to go with the manufacturer specifications first, and then we'll go from there. So I've got that, and I've got it going to a USB Type B connector. As far as power goes, most of the devices on this schematic use 3.3 volt logic, but first we need to regulate the power coming from the battery. And I do have some devices on here that use 5 volts. So I have first got a step down buck converter for the 5 volt level, and this is going from the battery voltage, which is really 7.4, but I just use 7.5 because that's what KiCad had in there, to a little switch mode module from Texas Instruments, an LM 2576, and we'll look at the data sheet for this in just a moment. And then I've also got that going to a LM 311, which is just being used as a comparator, and I'm using this to measure the battery voltage, and if the battery voltage drops below a certain level, then we will send a signal to the microcontroller to initiate shutdown of the rover. So let's take a look at the data sheet for the switch mode power supply module, and then we'll dig deeper. So this is the data sheet for the 2578 simple switcher power or voltage regulator. So this is the one that I'm using to produce my 5 volt rail, as you can see here. And again, I just use the manufacturer specifications for recommendation. I did add a few more filter capacitors for the fact that there's going to be some noise because we have some motors on this circuit. So I did add a few more capacitors and made sure that whatever components I select can handle the higher currents, which they're all going to be recommendation or built to handle the voltages and currents that this device can put out. This particular device can handle up to 3 amps. So that seems fairly sufficient for what we're doing. It's actually probably a little more than what we need, but I just wanted to make sure we had everything possible that we need for adequate control of the rover. So fairly simple. In this version we'll be using the this package type. So fairly simple. Just make sure that whatever device you use for your power control, that you take a look at the data sheet. I keep track of all the data sheets for the different devices, and I make a point for all the major devices to download all the data sheets for the respective parts. So that is our main power regulation. Then we have an LDO, which is controlling our 3.3 volt logic level, or power rail. And 3.3 volts is the majority of what's powering this device. So let's take a look at its data sheet real quick, just so we can get an idea. Alright, so for this, this one is an adjustable device, but I have it adjusted for 3.3 volts. Little SO8 package. So again, make sure that whatever you get matches whatever your needs are. This can also produce 3 amps maximum, so that seems fairly sufficient. There's not that many devices, but there are quite a number of devices that pull quite a high current at 3 amps, or hold quite a high current, such as the radio module and the cellular module. So I just want to make sure I have enough support for all those devices. Like I said, it's the main power rail for the entire rover, so I want to make sure I have enough power to do that. So now that we've got power, let's take a look at other peripheral hardware. Alright, so in addition to power, we're going to have quite a lot of servos. Ideally, I'm thinking about putting a robotic arm, so that's possibly up to like 6 servos, and then maybe a pan tilt assembly for a camera and sensor on the top or on the front of the robot. So that's quite a lot of servos, so I wanted to make sure I had enough PWM channels. And I'm not really sure how many PWM channels the ESP32 can handle or even put out. So for that reason, and plus not to eat up all my GPIO, I've decided to go with this PCA 9685. This is a 16-channel PWM driver chip, which can be controlled over I2C. The advantage is that you can get a multitude of different GPIO pins, or PWM channels, without eating up all your GPIO. And in fact, all you need is two of your I2C interface, but you can share that between multiple devices. So it seems like a win-win scenario. So here we are. I've just got it connected for the majority of the PWM channels to a pin header, which will connect to a port on the front of the rover. And then there's 4 channels that I needed for the motor drivers, because all of the motor drivers are PWM controlled. So I needed 4 of those. So that was another addition. And the great thing about this, since it's I2C, I can add another one if I need more PWM channels and get, have a total of 32. So it really is an advantage that I want to take. Like I said, I save all my GPIO pins. And this is actually an LED driver, so if I wanted to use this for like controlling LEDs around the rover, or have any other type of GPIO, like this can do like just on-off channels for the GPIO. They can't pull a lot of current on each channel. But let's say I needed more physical GPIO, I could even use it for that. But I don't plan on using it for that purpose, but that is an option if I ever needed to expand my GPIO. Although there's smarter chips for that too that can actually handle more current. But that's a topic for another video. But like I said, so we got the servo outputs, and they're being fed off the 5-volt rail. And this is a 5-volt device, or at least the one that I found. So because of that, I needed the ability to shift between 5 volts and 3.3 volt. So I've got this device down here, which is just a level shifter. So I have the I2C pins, and this level shifter, I made sure on the data sheet it can support I2C. You just have to make sure you still need the pull-up resistors on both sides so that you don't lose that, because I2C, you have to have pull-up resistors. So I still have the pull-up resistors, but on here I've added them to the output of the device, which puts them on the 5-volt end, and then on the on the other side, they're coming from the ESP32 module section. So, but in both cases, it's pulled up, so that's taken care of. Then there's some other GPIO that I'm using, and we'll talk about those too. But this shifts it up to the 5-volt logic level for this device, and allows us to use 5-volt devices. And there's still some available pins through this level shifter, so if I need more, then I can always do that. It's just relatively simple level shifter, but like I said, I just made sure that it can handle I2C. Some level shifters can't handle high-speed communication like that, but there's always caveats to it, And in this case, there is a caveat. Like I said, you still need to pull up resistors, but that's not a very big issue to fix. Alright, and so the next peripheral device is the motor drivers. So in this case, I'm just using PWM driven dual H-bridge motor drivers. So that's what we have here, the DRV 8872. Now these have 2 fault pin, or a fault pin that comes out, so if the motor drive faults, such as a short, it can trigger an alarm, and this is also going through the level shifter back to the 32. And then that battery signal that we had, because that was a 5-volt output. So in addition to the motors, we have the Fauna 808 module, which is our communication module to the outside world. This is a 2G cellular interface module, or cellular communication breakout board, with GPS capability. from Adafruit, and I just am going to mount it directly to the board with the pin header, and then just have the 2 screws that are built onto the board, or the 2 screw holes to create mounting structures to mount it to the board through standoffs. So that module, and then for short range and long range radio communication without using the cellular interface, we're using the LoRa radio module, just a little 900 megahertz radio transceiver, and I'm going to have to build a second device to also work as a radio transceiver on my end so that I can talk to the rover without having to break out the cell phone. The cell phone just adds additional levels of control because the rover is going to be designed to be semi to fully autonomous. So this allows me to do basic controls like start, stop, or give basic drive commands. But if I want to take direct control over the rover and drive it manually, then the LoRa radio module is what would be used in that case. So we have both. And the LoRa radio module uses SPI, so that's going straight into the ESP32. And for all other devices, I'm also going to put a pin header for the GPIO. So if I have other devices I want to add in the future, I can just play around with those. I briefly thought about adding things like a gyroscope and other sensors, but there's really not that much of a point. I mean, there kind of is, but I'm not really too sure if I want to add that right now. But that may be added later. So that's why I left this big opening here in the schematic page. And that's also why I broke out the GPIO, so I can add those sensors or devices in the future. I even added the communication lines so that I can utilize that. And if I choose to in the future make a second revision with added sensors such as gyroscopes, accelerometers, or various other sensors, then I would add them down here and then just connect them to whatever communication interface I need to add them to. So that's a little generic of an introduction to the schematic drawings. And the next phase of this is going to be designing the circuit board. And like I said, we're going to be sending the design off to JLC PCB to get it manufactured. So, and this will actually be the first time I've sent a board off to get manufactured. I've always done my own board manufacturing in-house, like I've etched my own boards, and they turn out great, but I just think that a professional board would be a whole lot cooler, especially now that it's so inexpensive and relatively easy to do today. So it makes much more sense, unless I have to have it tomorrow, that I can just have it manufactured from an outside source. So that's what I plan on doing, and over the next several videos, that's what we're going to be focused on. So I think it'll be very exciting. Like I said, this is just a little introduction, so there's not a whole lot of content to this video, but just kind of introducing you guys to the rover's board, control board, and everything. So let me know what you guys think about this board design, and maybe what you might change, or what you like about it, what you dislike about it. Everybody's entitled to their own opinion, and I guess it's a design decision that everybody can have. Everybody might have a different design idea from time to time. So my design may not be the best, and there's probably some flaws in it. Like I said, this is first revision, so there's bound to be some things that I don't have right. So I may have to make changes and redo the board design. But hey, it's a learning experience. That's what engineering is about. So I hope you're excited. So like I said, next video we're going to be talking, or start doing the board design process. So look forward to that. See you next time. Bye.